Hi, in this video, we want to take an initial look at spectral analysis and filtering on time series. Okay, so what is the big idea? Well, the previous models we were talking about autoregressive integrated moving average models. All right, so we were focusing specifically on autoregressive and moving averages to model our time series. Now, we want to get into a different structure for our modeling. We're going to take the point of view that we can sufficiently represent our time series using sine and cosine trigonometry functions. All right, and now if you look at plane time series, this makes a lot of sense. And what we're going to do here, we're going to take an initial look and we're just going to dip our toe, just the tip, into using sine and cosine of different frequencies to model what's going on. Now, what we're going to do is we're going to take those sines and cosines of different frequencies, and we're going to use those functions as our vectors in a regression approach. And so we're going to have a coefficient that we would normally put in the amplitude position in a standard trigonometry course, and those coefficients are going to be our regression coefficients. That's where we're going. All right, now we're going to run through some examples from time series analysis and its applications. Here are the names of the authors. Here's our GitHub page. And students at the University of Central Florida can download the textbook for free. All right, so here we're going to start, basic trigonometry stuff. All right, so a cycle of one complete period of a sine or cosine function defined over a unit interval. All right, so we're going to define a cycle as one complete sine wave for sine or cosine. So now consider the periodic process that we have. So let's say that I have my time series data is strictly a sine or cosine function. Here I'm printing out cosine, but sine would work out perfectly well. Well, here we're going to have A is the amplitude. That's the magnitude of from baseline of the height and the lowest points of the sine wave. Here we're going to have 2 pi times omega times time plus this phi. This phi is going to be our phase shift, and omega is going to be the frequency index in terms of cycles per unit time. Now, remember that the standard period of regular old sine, regular cosine are 2 pi. And so here, what we're doing is that we're setting it up just to make things more consistent and easier to interpret, is I'm putting in that 2 pi coefficient in there. All right, well, if I think about this, I've got some trigonometry tools to work with that I notice that I've got a trig function on a sum of angles. Well, sum of angles, we have a formula for that. And so what I'm going to do, I'm going to represent this process in a format that's better suited for the purpose of statistical analysis, because it will be easier for me to find the parameters for estimation. If I was to go in this format here, this phase shift term is on the inside of a nonlinear function, and I'm going to have to use more advanced techniques to be able to fit and find that parameter. But if I do a little bit of trigonometry, easy peasy lemon squeezy, things are going to be set up easier for the purpose of statistics and parameter estimation. So let's go ahead and use the sum of angles formula. And remember, we have a formula for sine and cosine. Honestly, we don't really care which one we're using at this point. This is just to give us an idea of what's going on. Also, we could approach this as cosine or sine either way. It will work out, because remember, if I do the proper phase shift, I can get a sine wave to be represented as a cosine, or a cosine wave to be represented as sine. All right, so when I apply my sum of angle formula, I know that I'm going to get this formula here. All right, now if I look at this, A and phi are constants. Okay. A and phi are constants. Therefore, the sine and cosine aspects here are both constants. So you know what? I'm going to replace this with a constant, because I don't know what A and phi is anyway. I don't know what A and phi is anyway here, so I'm going to replace this with a u sub 2. All right, now in this representation, you'll notice that I've got a coefficient times cosine, and I've got a coefficient times sine. Okay. And so here, this is what my u1, u2 are defined as. And my amplitude squared will be the sum of the squared coefficients. And if I want to figure out what phi is, I can figure out what tangent is by taking the ratio of the coefficients. And then I could go on further to use arctangent, the inverse function. And I left it as just tangent because it's possible for phi to be on different periods depending on what my project would be or what different locations for phase shift. So I left it as that to make it as general as possible. Now, something that's important to notice is that all of these are constants with respect to time. So here, I'm going to be actually wanting to estimate these values, but time is going to be independent of these. Now, one thing that we're going to do is typically we're going to say that U1, U2 are normally distributed, just like in the rest of statistics. All right, so if that's the case, we're going to get a really nice result that A and phi are independent, with A squared being chi-squared distributed, phi being uniform, negative pi to pi. Notice that is a full revolution around the unit circle in radians. If and only if the U1, U2 are independent standard normal. All right. All right, so let's go ahead and run through the proof. This proof is pretty standard if you take theoretical statistics. If this proof is very, very similar to what we have to do to show that the normal curve defines a probability distribution, because we have to convert over to polar coordinates. All right, so let's go ahead and say that U1, U2 are standard bivariate normal with zero correlation. Okay, well, in that situation, our independence gives me that zero correlation, by the way. That connects up to the independence, because zero correlation and normal is the same as independent and normal. All right, so here I'm just writing out the bivariate normal of the situation I've got. All right, so I just put that down. Now, let's go ahead and say that A and negative phi, notice that it's not actually phi, it's negative phi because of that negative sign that I had in my sum of angles formula. Well, if I say A and negative phi are the polar coordinates, then U sub 1 is equal to this, which is A times cosine of phi. U sub 2 is A times negative phi inside sine, which, remember that sine is an odd function, cosine is even. And so just boom, immediately I get these results. Now, I've set up this distribution. I want to use this to figure out what is the distribution of A, what is the distribution of phi. Okay, standard math problem for statistics. So what we're going to do, I'm going to replace U1 and U2 with their substitution. But remember, I always have to have that rescaling aspect. So I need to use the Jacobian. All right, so when I use the Jacobian, remember that I need to take partial derivatives, and then I need to take the determinant of the corresponding matrix. All right, so when I do that, just going through and just slugging through, simplifying this out, I notice that this is going to be negative A. So now I'm dealing with a probability distribution, so I know that I want a positive value. So this is going to get replaced with just A, because an A is an amplitude, so I know it's going to be a positive value. And so now I end up getting my two-variable probability distribution. Now, if you look at that, you'll notice that, hey, You said there's two variables in there. It's supposed to be for A and phi. You're right. There's no phi in there. This distribution is constant with respect to phi. That means we've got uniform distribution. Immediately, we see that very quickly. All right, so I've got uniform distribution on phi. Well, what's the range of it? Well, by the construction of phi, I know it's going to be from negative pi to pi because I'm dealing with the trig functions to set this up by how I got here. Now, we're going to take it a little bit deeper, and I need to consider what is the distribution of that I'm looking at with respect to A. Well, this is almost a gamma distribution, but I've got a square up here, right? So then if I look at that, I go, you know what? I could rewrite this. I can replace this A as a square root of A squared. And if I leave this in this position, and I work all this out, oh, there should be a, no, that's good. Yeah. So as I work through this, I'm going to notice that in fact, if I do a little bit of manipulation on the exponents, this is in fact a chi-squared distribution, and I get exactly 2 degrees of freedom if I'm looking at A squared. Huh. All right. So that is interesting. That is good to go. And so because we have constant with respect to phi, I know it's uniform. Here is the rescaling value that gives me, so I can see what the value is here. That here is the uniform aspect. And then I know from what I've built up that I've got 2 degrees of freedom on the chi-squared. All right, so now in the actual modeling, we're going to actually go a little bit looser on this, in that we're just going to say the use of 1, use of 2, we're just going to say those are 0 correlation. And we're not going to be so rigid on what the distribution is. We're not going to actually assume that they're independent. But we are going to say that the expected value is 0, and the variance is equal to just sigma. We're just going to slap that down for theoretical results. Now, from the setup that I've done, just off of this portion, it's going to work out that we have a stationary x sub t by how we've constructed this so far. All right, so now let's go ahead and calculate the autocovariance of my process. All right, well, if I'm going to sit through and calculate the autocovariance, that's just going to be the covariance of my process at different time points. All right, so then I copy and paste for the formula into here. So here's x sub t. Here's x sub t plus h. Now what I'm going to do, I realize I have covariance of a sum and a sum. All right, so I can simplify this by breaking this up into 4 sub covariances. And so I've got a covariance here. I've got a covariance here. A covariance here. And then it's so wide it won't even fit on the screen. I've got a covariance here. So what's going on? This term here, I'm going to have a covariance here. And I'm going to have a covariance between these two. I'm going to have so that's my second covariance. I have a covariance between these two. That's my third. And I have a covariance between these. All right. So I've got a total of 4 covariances. So now I'm going to look at this and I realize, well, what do I have? Remember, I'm going to be treating u sub 1, u sub 2 as my random variables. And time is a constant. And omega is a fixed parameter for this. And so omega is constant, time is constant. So my trig functions are all constant values for the purpose of this calculation. Those are all constant. So now I'm going to take those and I'm going to pull them out because they're not random for the purpose of the covariance calculation. And so I'm going to end up getting covariance of U1 with itself, covariance of U1 with U2, covariance of U2 with U1, and then the next one will have covariance of U2, U2. All right, so now I remember, hey, didn't we assume that we had 0 covariance between U1, U2 right here? Yeah, we did. We made that assumption. So I know that those middle two covariances are going to be equal to 0. Furthermore, we said that the variance of U1 and the variance of U2 is equal to sigma squared. I can replace both of those. So here, I get 0 and 0 from 0 correlation. This is going to be replaced by sigma squared. This is going to be replaced by sigma squared. And so now a lot of things have simplified out. And I realize that, in fact, I've got something that looks a lot like a sum of angles formula. So it's actually, this is the difference of angles. This is I recognize this as, in fact, I have cosine of two different angles plus sine of those same two angles. All right, from my trigonometry class, I know that this is cosine of the difference of the angles. So I'm going to take this angle, subtract this angle, and I know it's going to be on the inside of cosine. Boom, I've got this. So, all right, that gives me my autocovariance for my x sub t when we only have one trig function involved. And so if I want to get the variance of the overall process, I just slap in h equals 0, and boom, I can see, remember, cosine of 0 is 1. I just get sigma squared. Huh, isn't that nice? All right, so now, one thing that we could do as an estimate of what's going on, I could actually use the sum of the squared values of my estimated parameters as variance estimates on the entire system based off of what we're talking about. All right, so now let's talk about the folding frequency. All right, so a random process is a function on omega. So omega is a hard fixed number. It's a parameter. It's not random for our purpose. All right, so if omega is equal to 1, the series makes 1 cycle per unit time. If omega is equal to a half, it makes 2 cycles per unit time. If omega is equal to 1/4, it makes 4 cycles per unit time, and so on. So this is going to be important to us. All right, so going forward, when we decide what trigonometry functions and what omegas we're going to consider in terms of fitting in that regression process I talked about earlier, we're going to need at least 2 points to determine a cycle. So the highest frequency of interest that we can get is 1/2 of the cycles per point. So that's going to come up later when we are computing our periodograms. All right, and so this frequency is called the folding frequency and defines the highest frequency that we can detect in our discrete sampling. And so if I have fewer points than what's actually going on in the system, I will not be able to detect it and determine what's truly going on. All right, so this leads to the concept of aliasing. Aliasing is when I'm not sampling fast enough to detect on what's going on. A good example of this in real life is when you're watching a video of, let's say, a helicopter rotor spinning, and you see the beginning of, or you see the helicopter sitting still. It's not the rotor is not spinning yet, and you see that's going in a particular direction. Then, as the video progresses, it looks like the rotors are actually going the opposite direction. That's because the frame rate of the video is not fast enough to detect where the rotor is effectively, and because of the insufficient sampling, it looks like it's going in reverse when in reality it's not. The same thing can happen with cars going down the road, that I can see a car that's moving fast enough and it can appear that the wheels are going in reverse as the car goes down the road. All right, so higher frequency sampled this way will appear at lower frequency. This is called aliasing. For example, most movies are recorded at 24 frames per second. If the camera is filming wheels that are rotating at 24 hertz, the wheels will appear to be standing still. All right, and so here, where we're going with this is I want a more general model than I did. So previously we talked about just one trig function. Now I want a whole collection of trig functions. And so taking one trig function, I can get a sine and cosine being multiplied by a coefficient. And so what that will lead to here, if I want a collection of trig functions, well, I'm just going to basically do the same trick on each of the individual ones to break it up in two parts. And I see that if I want to get a summation of trig functions, this is a natural way for us to approach. And we're going to say that each of the pairs of coefficients are uncorrelated with each other. We're going to say that as I'm approaching this, as I'm trying to figure out the parameters of the system, the expected value will be equal to 0, and the variance will be equal to a constant between those two. So notice that the variance can change for each of the different indices. You notice that here, for each of the different omegas, we can have a different variance. All right, so now what I can do, I can take the concept that I just did previously with the calculations for covariance and whatnot, and repeat exactly what I did for this process here. All right, well, if I do that, here I'll get the auto covariance of the system. It's going to be very similar to what I had before, but now I've got multiple indices going on, multiple omegas, and they're being all added up. Here we get an upper bound and a lower bound on the covariances, auto covariances. And we also get another way to estimate the variance overall. Now, when we have smaller values or smaller Q for this, just from, yeah, this isn't coming from a paper or theoretical resort, but just my observations is that frequently we would like to divide the estimate by 2 to get an improvement. I'll justify that in a moment. This is not in the textbook, but here, this gives us an estimate of the variance of the overall system. And in my opinion, when Q is small, we should divide by 2. The textbook just gives this value here and doesn't talk about rescaling at all. All right, so let's take a look. Let's go ahead and say that we have Q is equal to 6. And we have, or it's actually equal to 3. We have 6 total trig functions in the mix. And this is my true process, is that I've got, here's my V. I'm kind of shortcutting a little bit of the code, make it easier to read. And I'm rescaling by 6. It should technically be 6 over 100. 6 over 100 for my omega, 10 over 100 for my omega, 40 over 100 for my omega. And then in my process, I've got 3 different individual, 3 total things coming in together. All right, so here I want to take a look at the first one with omega equal to 6 over 100 from what we generated, and we can see that this is our amplitude squared is equal to 13. Looks a lot like a regular old sine wave, but it's not quite. Here, if I take the next one, here I've got the amplitude squared, and you'll notice that here it looks a little bit more angled. It's not, it's still a continuous function, so it's not, there is no angle on this. But, you know, we can see it's looking a little bit different than a sine wave. And so here now, if I go up to our very last one in that summation, we can see that it looks very different. from a sine wave, but we definitely see a periodic process very obvious to us. Now let's take a look at the actual process when we add them all up. Well, wow, look at that. That, you know, at first glance, you wouldn't even think that this is periodic. But if I take a moment and I look and I realize that, I can probably break this down into individual trig functions. All right, so let's go ahead and check that variance estimate that we talked about a moment ago. And so here, if I take the variance of x sub 6, you'll notice that it's pretty close to the amplitude squared added up, but I have to divide by 2 if I want these to get tight. It'd be pretty tight. Here, 10 over 100 for my omega, and we see that these two are pretty close if I divide the second one by 2. Here is the variance of what I have for my data, and if I divide the amplitude squared added up divided by 2, I get something pretty close. And so now, once again, things are the estimate, it would be improved if I divide by 2 every single time. Now, when I have larger Q, we're going to start having the trig functions cancel out with each other. And in that case, I don't need to divide by 2. All right, so now we want to talk about the periodogram. The periodogram is a visualization, a tool that we will use to detect what are the coefficients of the different trig functions and which omegas should I use when I'm actually going to fit my model. All right, so it's going to work out that if this is my data and n is odd, I'm going to have an exact representation. And it's going to be this. So when it's odd, subtract 1, divide by 2. All right, and then I'm going to have a constant value there. And then here, this will be my process there. And our goal for this is that I want to estimate a sub j and b sub j. When n is even, I'm going to make a little bit of an adjustment. That adjustment is that I'm going to take a sub n divided by 2 and multiply by -1 to the power of t. So I'm multiplying by plus or minus 1, and I'm just going to tack that on to there. And what we're going to be doing is that here's my exact representation of the system. I'm going to approximate what's going on using this formula here. Now, when I use the exact formula, it's okay for us to have a lot of coefficients close to 0. The coefficients that are close to 0 in the process, when I'm modeling, I'm going to assume that they're actually just equal to 0 to have a simpler process, because with real life data, I won't be able to tell the difference between noise and coefficients very close to 0. All right, so now let's go ahead and take a look at figuring out regression coefficients for those trigonometric functions. Now, before I can do this, I'm going to need a lemma. Remember, a lemma is a theorem that is useful for something else. So in theoretical mathematics, we're never interested in a lemma. A lemma is something we use to achieve something we are actually interested in. So there's a result we're going to be working on in a moment that we're interested in. This is just going to be a stepping stone to get us over to where we want to be. All right, so if n is an integer and I have an angle equal to 2 pi j over n, where j is an integer value and j over n is not an integer, then if I take that angle, and so I've got constant arc length around the unit circle, and I add up the x coordinates and the y coordinates along the unit circle like that, I'm going to get 0 for the sum of the x coordinates, sum of the y coordinates. And that's what I'm saying here. So this summation, this corresponds to going about the unit circle, a constant angle moving about the unit circle, take all the x coordinates, add up all those x coordinates. I am guaranteed to get 0 as long as I satisfy this for my angle of rotation. So take the unit circle, rotate an angle, rotate an angle, rotate an angle, so that I have n points along the unit circle, and the angle between points is constant. Then when I add up all the x coordinates, it's equal to 0. When I add up all the y coordinates of the points on the unit circle, it's equal to 0. And that's going to correspond to e to the power of I theta k, add all it up with respect to k, that's going to be equal to 0. By proving this, these two will come out for free because cosine will correspond to the real component, sine will correspond to the imaginary component in this summation up here. All right, and how do we do this? Well, as obviously as possible, this is the most natural proof to do this calculation. I'm just going to once again use a telescoping series. I'm just going to write it out, what I've got, multiply the top and bottom by what it takes to make a telescoping series. So I get to here, I've got a telescoping sum, and I realize, well, hey, by how I built this up, this is going to be equal to 1. Since it's equal to 1, this fraction has to be equal to 0 as long as the fraction is defined. So for the fraction to be defined, I need the denominator to not be equal to 0, which is taken care of by this part of the assumption. Boom, I've got it. All right, so now the next thing I want to show is that if I'm going to go and estimate the coefficients, I have a nice formula that will speed up the process for me. All right, so remember, so in a moment, I'm going to talk about estimating the coefficients of sine, the coefficients of cosine in the formula we talked about a moment ago. Well, remember in your standard regression course that when we're estimating the coefficients, we have a sum of terms squared on the bottom. Well, it's going to work out that that sum of terms squared is going to be equal to n over 2 every single time. All right, so here, when I do my formula for the regression coefficients, this is going to be on the bottom. This is going to be the denominator in the coefficient estimation formula. All right, well, this is equal to that. Okay, well, now I notice I've got cosine squared. Well, cosine squared, I have a nice formula for. Remember, this formula is critical to Calc 2 to be able to do my integration, so I recognize it. So I'm going to replace cosine squared with the appropriate formula. Now I notice here that I've got a summation of a constant plus a coefficient times cosine. Well, I'm going to bring that summation in, and I realize that, hey, this is going to be equal to 0, and the summation here is going to give me n over 2. Boom, I've got it. Now, something to notice is that this summation goes from 1 to n. The formula I talked about a moment ago in that lemma was from 0 to n minus 1. It's okay because that's effectively the formula for the lemma. If I was to do a rotation by one of those angles, I would be able to accomplish that, and I would get the same thing as I got here. But in the lemma, I did the simpler version to make it easier to follow. It's equivalent to multiplying by a constant in terms of complex numbers. I do exactly the same thing for sine, that if this is going to be my vector that I want to use as a predictor variable, when I estimate my coefficient, I'm going to need to divide by the sum of the values squared. Okay, well, that gives me this. And I recognize that sine squared, I have a formula for sine squared. And here the formula is very similar to the one we just looked at, except for instead of a plus, we have a minus. And then boom, it ends up being the same concept. All right, so now let's go ahead and look at our actual formulas for figuring out the coefficients. All right, well, here I'm going to take the dot product between what I observe and the vector that I want to do the regression with, and then I divide by the dot product of the vector with itself. All right, standard regression approach. Now, from what I just worked out a moment ago, that denominator is equal to n over 2. Dividing by a fraction, same as multiplying by the reciprocal, I get 2 over n right there. That simplifies things. This helps me speed up the computations nicely. We repeat exactly the same trick for sine. I know this is going to be n over 2 divided by a fraction, same as multiplying by the reciprocal. Boom, I've got this. So now things are a little bit cleaner, easier to work with. All right, so now we want to talk about the scaled periodogram. And so what we're going to do after I get those coefficients off of sine and cosine, my scaled periodogram is going to correspond to taking those coefficients, squaring them, and adding them up. And this is going to be a way for us to measure how important is a particular frequency for my time series values. All right, so now let's talk about the Fourier or fundamental frequencies. All right, so here we're going to say that our fundamental frequencies are going to be J over N. Now, why am I going J over N? Because I've got that 2 pi in there. Other textbooks are going to approach this without that 2 pi, or maybe just a regular old pi, depending on what they want to emphasize. So if you look at another textbook, things might be slightly different. You're going to need to be able to adapt if I'm comparing different books. So the scaled periodogram is a sample variance at each frequency component and estimates the variance at each of the corresponding frequencies. Larger values on the scaled periodogram indicates that the frequency is more important, more predominant for my time series, while smaller values indicate that the frequency might just be picking up noise and I don't really need it in my system. Fortunately, it's not necessary to run a large regression problem to obtain the values of the coefficients, because we're going to be able to use the Fourier transform to do this pretty quick. And so what we're going to do, we're going to invoke the Fourier transform and a fast Fourier transform to do this. We'll talk about these a lot more in future videos. So here is the discrete Fourier transform. I just want to whet your appetite for it just to show it. And so here, I'm going to find my discrete Fourier transform for the particular frequency. It's just going to be this particular value. Now, something that is important to know is that different textbooks, different packages, different authors, different journal articles are going to define this slightly different. And so we need to look at our documentation, look at our help documentation to understand what it is that we're trying to work with. Now the periodogram, and here I've got a typo in here. I will fix that after I post the video. Here, the periodogram is similar, but here you'll notice I'm taking the absolute value of that discrete Fourier transform. This is not the scaled periodogram. I'm taking the discrete Fourier transform absolute value, that is the modulus, because we're dealing with imaginary numbers, and then I'm going to square it. Now, something to realize is that we have a reflecting aspect in this process. Remember that whole folding idea we mentioned is that the value that we get on that scaled periodogram for J over N is going to be equal to the same value I get for 1 minus J over N, because I'm dealing with periodic functions. And so when I look at my periodogram, if I plot the entire thing, I'm going to have a symmetry about the plot. It's normal for us just to pick up half of the values just to shortcut things to make things easier for us to work with. All right, so now we want to talk about spectral analysis. So think about the situation where I have a color. I could interpret the color as being the composition of some primary colors. And the amplitudes correspond to how much each of the colors are putting in to those to the total color that I look at. And so this is where we get the idea of spectral analysis, because we're connecting it to light. All right, so let's go ahead and come up with an example. Let's say that I'm going to take the absolute value of the fast Fourier transform of that x we had a moment ago. And so every package has a slightly different representation of the fast Fourier transform. Here, we're going to be dividing by 100, multiplying by 2, and then after I take the modulus, I'm going to be squaring to get the periodogram. And then I can plot out what we've got. So the x-coordinate is the frequency, and the vertical axis is the periodogram. So here we can see that we've got 3 important components on here to worry about. And these correspond exactly with what we were talking about earlier very nicely. Now on this next example, let's say that I've got cosine, and I've got cosine, and they're being multiplied together. Now you'll notice I've got 2 different frequencies going on. Now, if I go through and I do my trigonometry, I've got the product of cosines, which I can change to the sum of cosines in this manner. So this is my product to sum formula. Okay, so now if I go through and do the calculation, this is in fact going to be it will be equal to this right here. When I take the x value and actually run my periodogram, so here's my actual observed time series. When I run through the fast Fourier transform and I plot the periodogram, you'll notice that it actually detects both of them here, of the 0.19 and the 0.21 are both detected, even though they're pretty close to each other. This is very nice. All right, now for the last example we're going to talk about, we're going to look at star magnitudes. And so the star data set from the ASTSA package, this has the magnitude of stars taken at midnight over 600 consecutive days. The data was taken from the classic text, The Calculus of Observations, a treatise on numerical mathematics. The periodogram for frequencies less than 0.08 is also displayed in the figure. And we'll note that the periodogram ordinates for frequencies higher than 0.08 and are essentially equal to 0. All right, so now when I look at this, notice that 29 is approximately 1 over 0.035. 24 is approximately, and this is an approximation, equal to 1 over 0.041. And these are going to be the most prominent periodic components that we have in this process. So what we're going to do when I model this, I'm going to say that I've got my time series is going to be equal to the trigonometric function aspect plus a stationary time series process. All right, and so here, my trigonometric portion is going to be omega times t inside cosine, and then delta, where the delta is relatively small off of this. All right, so now, in this situation, if this is my correct model, I can go in and convert the product, so the product of cosines into the sum of trig, so product to sum formula, and I know that I can rewrite this in this format. And you'll notice I've got omega plus delta, omega minus delta, And so here is my actual time series data. Here I'm taking the fast Fourier transform. Taking the modulus and squaring and dividing by the length of the data. Here I'm getting the frequency of what's going on, and then I'm going to go ahead and plot it. And so here we can see that we've got two really big spikes, and those two really big spikes are clearly the most important ones. And we look at that and we notice that one is going to correspond approximately to a 29-day cycle, and the other one's going to be approximately a 24-day cycle. And so this gives us a nice, good inference about the process of that individual star. And so now we can go through and look through what's going on here, on what's going on. And so here I see the 29 and I see the 24 are my largest ones, and we can, work with that from there. And if I wanted to pick up other ones, I could. Visually, I know that these are the most important. Maybe this would be one I would want to include. I would start with these two first, then consider adding this on. If I'm satisfied without it, I would leave it off. If it looks like it adds value to the model, I would tack it on, and then I would do forward selection on this one if I was going to model the star. All right, well, that's all I've got for you. Life is short. Do math.